Hello everyone. Let's continue. And the next job is to identify how does the change in the drain current affects the CMOS behavior. So ideally it should not, because that's what the expectation is, and that's why we say as CMOS inverter robustness, the CMOS inverter should be not much responsive, or it should be least responsive to the device variation, and that will make us to use CMOS inverter for the dynamic simulations or for any logic gate building. So that's the first thing we have to prove, that CMOS inverter is least responsive to device variation. So for that also we will do some spice simulation. We'll do some extreme spice simulations and see how does your spice simulation responses to the device variation. Okay, so the experiments that we have planned is something like this. You have your strong PMOS and weak NMOS. Let me take a minute over here to explain what is strong PMOS and a weak NMOS. When I say strong PMOS, it is the least resistant PMOS. So the PMOS is wider in size. The size of the PMOS is 1.87 micron. It's the widest possible PMOS available. Okay, and as a result of that, it's of least resistant. When I say least resistance, if it will provide a low resistance path for your output capacitance to charge. It's as good as R is equal to rho L by A. So as you increase the area, your resistance get reduced. In the same fashion, though resistance for transistors are not a linear function of your current, but I'll talk about that when we enter into the dynamic simulation course. Currently, if we have the strong PMOS, we will try to go by the original definition of a resistance, which is when you increase the size of your PMOS, your resistance reduces, and as a result of that, it's called a strong PMOS. Okay, in on the contrary, weak NMOS, it means that your NMOS resistance is very high, and we have taken the least value of your NMOS width, which is 0.375 micron. Okay, so this has got the highest resistance, this has got the least resistance, and we will assume that this is the highest and the least resistance available possible. So 1.875 micron is the highest width that can be fabricated, and 0.375 micron is the least width that can be fabricated. Okay, that's the assumption. And the spice simulation will start from this point, and it will eventually move to another point. This is the end point of your experiments, where we will use a weak PMOS and a strong NMOS. So when I say weak PMOS and strong NMOS, it means exactly the opposite what we explained over here. When I say weak PMOS, it basically says a least resistance for your the highest resistance for your PMOS, and when I say strong NMOS, it's the least resistance for your NMOS. Okay, so width of your PMOS is kept as 0.375 micron, and width of your NMOS is 1.875 micron, which is the highest. So we have to go from 0.375 micron to 1.87 micron for your NMOS, and we have to lower down the width of your PMOS from 1.875 to 0.375. Okay, and that's the experiment. So the experiment will be, we will sweep your WP from 1.875 to 0.375, and the reverse way for NMOS will sweep your NMOS from 0.375 to 1.875, and every step will draw the DC characteristics of the curve and see whether the DC characteristics of your CMOS inverter remains the same with whether or not you change this particular device. So it's basically the extreme conditions we are trying to test. The device variation concepts that we have learned till now, those are minimal. So we are trying to take your device to the extreme cases and see whether the spice simulation, how much responsive is the spice simulation to these variations. Okay, so we have the spice netlist we have already. So we will do some smart spice simulations over here. You have your NMOS, you have your PMOS over here, which is of the width 0.375 and L is 0.25 micron. I'm going to change this. I'll explain you that in a bit from now. You have your NMOS, which is of the same width 0.375 and L equal to 0.25 micron. And then, as explained in the previous videos, it's the dot control. Anything that comes under dot control, which is dot control and dot NC, dot NC is present over here. Anything that is in between them, those allows you to do some scripting. Okay, just like tickle. So you let your NMOS width to be 0.375 because that's what we want it to be, and your alter is an attribute or a construct in spice that helps you to alter the width of your NMOS. Okay, similarly for PMOS, width will start from 1.875 as we have discussed in this particular case. So we'll start from the strongest PMOS and alter the M1 width, the MOSFET, the PMOS width from from 0.375 to 1.875. Okay, that's what this alter constructs does. So we did explain about the alter in the videos in the past. You might want to have a look into those videos. And now we will let the width variation be 0. So this is just a variable that we are trying to set, and we'll do 5 iterations of it. Okay, we will try to vary the width of your PMOS and NMOS at steps of 0.375. Okay, so this is what it will do. First we'll set a variable called as width variation of 0, and we'll try to loop through this complete simulation. We'll try to do 5 different simulations for this particular case. So in this case, width variation is 0 until it hits the limit 5. We'll do the spice simulation. Okay, and we will, these are just some documentation for the simulations. We'll echo the NMOS width at each step, we'll echo the PMOS width at each step, and see what does it do. And for the same NMOS and PMOS width, we're going to do a DC simulation. So in this case, the first loop will do a DC transfer characteristics or the spice simulation for a PMOS width of 1.875 and for an NMOS width of 0.375. This is exactly what we wanted over here. Okay, and finally after we will increase the PMOS NMOS width by 0.375 micron every time we enter the loop, and will decrease the PMOS width by 0.375 every time we enter the loop. And we will alter the NMOS and PMOS width by this constructs, and will increase the width variation variable by 1. Will increment the width variation variable every time by 1. Okay, and the rest remains the same. We'll plot the DC characteristics. And since in this case we are going to do 5 simulations, we'll plot DC1 out versus in till DC5 out versus in. Okay, and rest all remains pretty much same. You have your VDD definition, you have your V in definition, and the dot level inclusion. Okay, so I have the spice simulator open with me. We'll go to this particular area where we have the netlist available. Okay, so we'll cd to this area, we'll source the circuit file. So this is the circuit file, device variation experiment. This is circuit file. We'll source this, and this is what you get. So you get this particular curves for each and every. So you have DC1, which is 1.3, which is the strong PMOS and weak NMOS. So DC1 is this one. Okay, and this is the DC5, which is weak PMOS and strong NMOS, and all the other curves are lying within them. So so let me stop at this video. From the next video, which will be the last video, we'll try to analyze what we did over here. We'll try to analyze all these curves and how much is the variation. Let us try to quantify all this in the next video. Thank you.